Okay, before I get into material and stuff, let's just figure out what's all coming up. So we have the quiz today. It's too late to get ready for that, so I don't have to talk much about that. But exam 1 is Monday. The 19th. If you'd rather go to the day class for the exam, the day class is Tuesday, the 20th, at 2 o'clock in room S1328. The quizzes, are just short answer questions about the lectures. You get ready for those by just going over the lecture notes a lot. These exams are nothing but problems, so the way to get ready for those is those practice problems. And the topics on exam 1 are, well, I should make sure. Okay, so it's just going to be units, measurements and units, and then particle kinematics along a line, just those 2 sets. And the best I can do to describe when you know you're ready for the test is the questions aren't going to be the same questions, obviously, but I would say if you get to the point where you could explain how to do these questions to somebody else who didn't know how to do them, like you could explain why, like, okay, here the thing we've chosen the positive direction up, and the thing's going down, and that's why it's negative here. If you could explain all those, every decision that you make to do the solutions in these problems, then you're going to do great on the test. Okay, the test is going to, all those questions are going to look very familiar. They're, it's going to be objects rolling and balls flying, and it's going to be all the same kind of stuff. It's just not going to be the same questions. Okay. Any questions about, yes? It depends on how many I do of each one. Like if it's units and measurements questions, there'll be a lot more. If it's, so it's hard to say, but somewhere like, I think what I can say useful is about that is I'm going to write the exam with the intention of half of the people in the class having turned it in and left by 7 o'clock. That's my plan. So I'm going to write it as an hour test. Some people stay the whole time, but my hope is that no one who is prepared for it will feel like it was a rush, like that's always my goal. Yes? Yes, all equations will be given and all conversions will be given. You just need to know how to use that stuff. Yep. We haven't done a test yet, right? No. This is the first test. Correct. Okay. I've done tests before, but that was years ago or whatnot. So yes, there's going to be units on it. Every test is cumulative. So there's potentially there could be unit stuff on every test, But
is it basically everything in our notes up to free fall?
Up through free fall. So we're not done with the stuff yet.
So free falls on there too?
Yes. Everything up until vectors, which is the next thing we're going to do.
Basically everything except for like.
Everything. Everything, even including most of today.
Okay. Always stop at the practice problems, trig and vectors.
Right. Yeah, don't worry about those yet. Any other questions? All right, well, today let's just, most of the time we're going to spend doing free fall problems. I'll do some, and then I'll write a couple up and give you time to work on them together. So the first one, a ball's thrown straight up. At 10 meters per second from a height of 3 meters. Did I do this one already in this class? Yes. Let's not do that again. How about this one? Did I do the one with the Franklin Bridge in this class? Yes. Okay. I got more, though. Okay. A ball is thrown straight down from the top of a 10-meter wall. And it takes 0.7 seconds for the ball to hit the ground. I have to get this picture right. Takes 0.7 seconds to hit the ground. The wall is 10 meters off the ground, so this distance is 10 meters. That's not drawn to scale, or else that guy would be like 40 feet tall. How fast was the ball going when it was released? Do you want to try it? Yes, I think that's a good idea. So work on this together. Compare where you're at, steps along the way, and then when you're done, I'll go through it. And you can, the benefit of that, I think, is if you go wrong on the solution, you can see where you misunderstood something. So first we're going to choose the time equals 0, the time final, the position equals 0 location, and the positive direction. What do you want to choose for time equals 0? When it's released, yep. And what do you want to choose for time final? Yep, right. Just before it hits the ground. And position equals 0. There's probably two sensible choices. I tend to choose the ground, so I'm going to do that. And then it's a free fall problem, so let's choose the positive direction up. Any questions about those? And then I'll go through the list of variables. Do we know the time final? Yes. What was that, 0.7? So time final is 0.7 seconds. Do we know the acceleration? Yep. Since positive direction is up, the acceleration is negative 9.81 meters per second squared. The initial position? And that's positive. Do we know the final position? Yep. Do we know the initial velocity? Good. And final velocity? We don't know. We don't care. So now we're looking for an equation that works with these. It looks like this should work. PF is equal to PI plus VITF plus 1/2 A TF squared. So it says how fast was the ball going when it was released, and the instant it was released was what we chose as time equals 0. So if it had asked how fast was it going right before it hit the ground, then that would be the velocity at our time final, and then that would be VF. Okay, so 0 is equal to 10 meters plus 0.7 seconds times VI, which we're looking for, plus 1/2 times negative 9.81 meters per second squared times 0.7 seconds squared. And so that's 10 meters. Plus 0.7 seconds times V initial. All of this comes out to be negative 2.40 meters. And so I'll move 0.7 seconds times VI over to the left side. Have to subtract that from both sides, so negative 0.7 seconds times VI is equal to 7.60 meters. And now divide both sides by 0.7 seconds. VI is equal to, so 7.60 meters divided by negative 0.7 seconds. And you get negative 10.86 meters per second. Yep.
So in general, I know you don't care about significant figures. So like, if it's like, I have like 10.853, like, you
Yeah.
would obviously
Right.
do it like, okay.
Or 10.9, either of those is fine with me. Yes?
So why would the final velocity be 0 since it stays the ground?
Yeah, so that's a because these equations only work for things that have constant acceleration. And this only has constant acceleration during the free fall part. And free fall means that it's not touching anything else. So our equations don't work once it touches something. I don't want to go through the calculation of what V final is, but is V final going to be, so what do we know about V final? Is it going to be positive? Is it going to be negative? Is it going to be bigger absolute value than this, smaller absolute value? It's going to be, so negative or positive first? Negative. It's still going to be going down. And the absolute value is going to be bigger. It's going to be like a bigger negative number. And how do you know that? So what that's saying is that it's speeding up in the negative direction. So how do you know that it's going to be speeding up in the negative direction? Yes, so acceleration and velocity have the same sign, so it's speeding up. Okay, so you know, we don't know without calculating what it's going to be, but it's going to be negative 15 or negative 20 or negative 25 or something like that. And if you were asked to calculate the final velocity, you could use that kind of thinking to sanity check your answer. Okay, let's do another one. So this is one where you're going to have to use an intermediate variable. We haven't done that before, but remember that if you go through, you choose the time equals 0, time final, the position stuff, and then you list out what you know and what you want, and then you look at the equations and no equation works, then the way you deal with that is you solve for something else that might be able to help you then find an equation that works. And that other thing that you're finding is what I called an intermediate variable. And there are really only two choices of those that ever come up, TF or A. Okay, so what you're going to do in this problem is when you get to the point where there's no equation that works, you're going to either find an equation that lets you solve for TF or find an equation that lets you solve for A. Figure out what that is, and then go back and try to solve for the thing you're asked for. Okay, so a ball rolls up a ramp. And there are 2 points, A and B. When it gets to A, the ball's speed is 5 meters per second. And then when it gets to B, its speed is 3 meters per second. And we want to first calculate how long does it take to go from A to B. All right, is this a free fall problem? No, because it's touching the ramp, so that's just the end of it. If it's touching anything, you know it's not free fall. That means we don't know what the acceleration is. Okay, so see if you can do this one. Work together, and then I'll do it when you're done. And then we'll do a couple other, I'll ask a couple of other questions about this scenario after that. So time equals 0, time final, position equals 0, and positive direction. Time equals 0, I'm going to pick when it passes A. Time final is when it passes B. And position equals 0, I'll choose A. In the positive direction, I'll choose up the ramp. Do we know a value for time final? No, that's what we want. Do we know a value for the acceleration? No, because it's not free fall. Do we know an initial position? The position when time is 0? Yep, PI is 0. Do we know a final position? Yeah, that's when it gets to B, and the distance is 1 meter apart, and it's going in what we chose as the positive direction, so this is going to be plus 1 meter. Do we know V initial? Yep, the speed is 5 meters per second, and it's moving in the direction we chose as positive, so that's plus 5 meters per second. And then V final. Yep, that's a speed of 3 meters per second, still moving in the positive direction. And so that's everything we know and want. Are there any equations that work? No, because how do you know that? Because I told you there's not before you started. So that means we need to choose an intermediate variable. We would need to solve for some other variable that then we can put in the no column and use to, sort of bootstrap our way to solving for TF. What's going to be our choice for intermediate variable? Yeah, so we want to solve for A because we know it's going to be one of these two, and we're already trying to solve this one. We'd do that if we could. So is there an equation that works that's going to let us solve for A? Yeah. 2A times the quantity PF minus P initial is equal to VF squared minus V initial squared. So 2A times the quantity 1 meter minus 0 is equal to 3 meters per second, all squared, minus quantity 5 meters per second squared. And so that says 2 meters times A is equal to 9 meters squared per second squared minus 25 meters squared per second squared. So 2 meters times A is equal to negative 16 meters squared per second squared. And then divide both sides by 2m. So A is equal to negative 16 meters times meters over seconds times seconds divided by 2 meters. One of those meters cancels. And you get an acceleration of negative 8 meters per second squared. All right, so are the units right? Yeah, so that's a good sign. And then the other thing you can usually compare to your intuition is, does it make sense that that acceleration is negative? It does, because this is moving in the positive direction and it's slowing down, so the acceleration has to be the opposite sign. Okay, so now we still know all this stuff, and now we know acceleration too. So we want to find PF. We know the acceleration is negative 8 meters per second squared. P initial is 0. P final is 1. V initial is 5. V final is 3. Is there an equation that works with these? I think it's the simple one, the one we always hope is going to work. So V final is equal to V initial plus ATF. 3 meters per second is equal to 5 meters per second plus the quantity negative 8 meters per second squared times TF. And I'll subtract 5 meters per second from both sides, and we get negative 2 meters per second is equal to negative 8 meters per second squared times TF. Divide both sides by negative 8 meters per second squared. So this is negative 2 meters over seconds divided by negative 8 meters with seconds times seconds in the numerator. The negatives cancel, the seconds cancel, and you get the time final is point. The meters cancel too. And you get the time final is equal to 0.25 seconds. Any questions about that? Yep.
So why isn't the seconds on top? Or why are they?
How did they end up on top? Just because when we divided by meters per second squared, that's like multiplying by 1 over negative 8 meters per second squared. And so everything switches, and you end up with seconds squared on top, and then one of those cancels. Any other questions? All right, so for part B, if you kept watching this as it went, this ball would roll up the ramp, keep slowing down until it got to a velocity of 0, and then it would start accelerating down the ramp, speeding up, going back down. Okay? So, after the ball turns around, what's its velocity when it gets back to point A? Okay. Take a few minutes and try to work through that. Okay.
Prove me wrong.
Okay. I certainly will. Okay, so time equals 0. That's when it reaches A. Time final is when it gets back to A. No, it's going. So here's A. Here's B. It's this ball rolls up the ramp, turns around somewhere up there, and then comes back, and eventually gets back to A.
So at time 0, wouldn't it be when it's turning around?
Yeah.
You don't have to do that. It's going to be easy. We're going to keep time equals 0. You could do it that way, but it's harder. It just takes longer. So we're going to choose our time equals 0 to be when it passes A the first time, and our time final to be when it passes A the second time.
So we're doing the whole track, not just like the second half.
Right. So time equals 0 reaches A on the way up. Okay. And then p equals 0, we'll make that a again. The positive direction will make up the ramp again. And then think about what we know and want. Do we know time final? No, we don't care. Do we know acceleration? Yes, we have to use the fact that it stays the same the whole time, and it does. Negative 8 meters per second squared. Do we know the initial position? 0. Do we know the final position?
Yes, 0.
0 again. Anybody have any questions about that? Do we know the initial velocity?
Yes.
Initial velocity is 5 meters per second. That's given in the problem. And then do we know the final velocity? No, that's what we want. And the equation that works with this is 2a times the quantity pf minus p initial is equal to vf squared minus v initial squared. So 2 times negative 8 meters per second squared times the quantity 0 minus 0, that's interesting, is equal to v final squared, what we're trying to calculate, minus 5 meters per second squared. All of this goes away because we have 2 times negative 8 times 0. So we just have 0 is equal to Vf squared minus 25 meters squared per second squared. Okay, so add 25 meters squared per second squared to both sides, and you get 25 meters squared per second squared is equal to Vf squared. And now take a square root of both sides, and you get that Vf is equal to, well, there's a 5 meters per second, but what am I missing? Yeah, it's plus or minus because we took that square root. And based on what we're dictating about this problem, which one of those do we want? The negative, because it's going down the ramp now. So the final velocity when it gets back to A, it's going to be 5 meters per second going down the ramp. So the speed is the same, which is, it must have taken me like all day to come up with a problem that worked out like that. But no. In fact, if you have constant acceleration and you have something that goes one way and then uses that constant acceleration to go back the other way, all the speeds are the same at every checkpoint back along the way.
Can you repeat that?
Yes. So anytime, some of these constant acceleration problems, like free fall problems and like this, are ones where you start out one direction, slow down, stop, and then come back the other way. And in those kind of problems, one of the characteristics of constant acceleration is at every point on the way back, the speed is the same as it was on the way up at that point. Just negative, the opposite direction. So what's the velocity when it passes V on the way back down? Yeah, negative 3 meters per second.
So if you graphed it, it would be a parabola just like how you just did, right?
Yes, and what that says is the velocity, this velocity is equal to that velocity. It's a property of the symmetry of the parabola, yeah. Yes?
So with that being said, if it's the same at each checkpoint,
Mhm.
your question was what was the velocity when it was going from B to A? and we found the velocity at A. So what's the velocity?
What was my?
-3?
This was what I intended to ask. After it turns around, what's the velocity when it gets back to point A?
All right. For some reason, I wrote B to A, so that's why I was like, no. Okay, got it.
Okay, so, well, one question. One thing this tells you is why it's not super safe to shoot guns straight up into the air. Because, I mean, there's a lot of air resistance on a bullet because it's going really, really fast and it's not that heavy. But if you ignore air resistance, you shoot a bullet into the air, and when it gets back to the height that it was shot from, it's going exactly the same speed that it was when it was shot, which is a dangerous speed. Any other questions about that one? Yes?
Okay, so one more thing. So the speed is the same at all intervals, just the sign changes.
Yeah. So bringing up the position versus time graph was a good thing to bring up. So what it's saying is we're talking about position versus time graphs that look like this. And you can see that this parabola is symmetric. What that's saying is the slope of that is equal and opposite to the slope there. The slope here is equal and opposite to the slope here. Right. Let's just take the quiz.